Welcome back. So in the last video, we did the discrete time Fourier series, and that was meant for the periodic signals. What if our signal is not periodic? It is non-periodic. So in that case, we have the discrete time Fourier transform. Just like in the continuous time case, your signal is periodic, so we can use the Fourier series. And if it is non-periodic, we have to use the Fourier transform. So same thing goes for the discrete time case. And again, just to build up the relation, what does the transform look like? We'll again use the same approach that we used in the continuous time case, where we assumed a non-periodic signal as a periodic signal with infinite time period. Fine. So what I will do here is that I will define a signal. Say let x tilde n, let it be a periodic signal with a period n, and let n is equivalent to 2m plus 1. It has this many samples. And from this periodic signal, we define a finite duration non-periodic signal. Call that x of n. And it will be actually one period of x tilde n. Right? So it is something like this, that we have a non-periodic signal x of n, which is equivalent to x tilde n over one period, that is from minus m to plus m, and outside this range it's going to be 0. Now graphically it can be something like this. This is your x tilde n. It ranges from minus m to plus m, which means there are 2m plus 1 points. Then it repeats, like I said, like you can see, this is repeating multiple times. Right? And from this signal I'm taking one period from minus m to plus m, and that becomes my x of n. Right? Now we can take the limiting cases. So we can say that as m increases, in other words, if we assume that this point is at minus infinity and this is at plus infinity, fine. So if we assume that these points m is farther distant from the origin, so as m increases, job k replicates the periodic replicates of x of n, which are actually present in x tilde n. They will move farther and farther from the origin. Fine. So under a limiting case, I can say that my x of n is equivalent to x tilde n for the case as m tends to infinity. Because as m tends to infinity, this will go to minus infinity, this will go to plus infinity, and these two waveforms, they will be quite similar. Fine. Now since x tilde n is a periodic signal, we can very much use the discrete time Fourier series. So we'll define it over the time period that starts from minus m to plus m, a k e raised power j k omega naught n. Right? And the coefficients, they will be equivalent to 1 by n. The time period here is 2m plus 1. Then the summation n runs from minus m to plus m, and the signal x tilde n e raised power minus j k omega naught n. Right? So now we may slightly reframe it using the conditions that kind of relate is x tilde n with x of n. Now first thing is that if you take the range minus m to plus m, that's from here to here, and in this range x tilde n is the same as x of n, right? So since the summation is defined from minus m to plus m, so we can very much use the substitution here that in this range, that is over a single period, we can replace, so in this range we can replace x tilde n by x of n, because within this range the two are the same, right? Then again, since we have now x of n, in general x of n is non-periodic, but we can assume it as a periodic signal if we change the limits from minus infinity to plus infinity. We use a similar approach in continuous time case. So what I'm doing here is we are assuming x of n is a periodic signal but with an infinite period. So again, with that change, the expression will look something like this: n is equivalent to minus infinity to plus infinity, right? X of n e raised power minus j k omega naught n, right? Since x of n is defined only from minus m to plus m, and outside this range the values are zero, so I can extend the summation in a more general way from minus infinity to plus infinity, right? So let's call it 1, fine. Now I will define a continuous function. I can define a continuous function of frequency x e j omega naught as this expression, and runs from minus infinity to plus infinity, x of n e raised power minus j omega naught n, fine, which means from this, the function that I have just defined, I can say that x e j raised power k omega naught, it will be summation and runs from minus infinity to plus infinity, x of n e raised power minus j k omega naught n. So this is an arbitrary function that I am defining, which is a continuous function of frequency because it involves the parameter omega. Okay? Now I can express a of k in terms of this expression, this function that I have just defined. So continuing with the analysis, I can say that a k is equivalent to 1 upon 2m plus 1, and for this n is equal to minus infinity to plus infinity, x of n e raised power minus j k omega n. I will make this substitution, so it will be x e raised power j k omega naught, fine. Now a of k is in itself a part of this expression x tilde n, it involves this a of k. So substituting here, what I will get is that x tilde n is equivalent to what to say, summation k running from minus m to plus m. Then for a of k I will use this expression, that is 1 upon 2m plus 1 x of e raised power j k omega naught. Then it has its own exponential, so we'll also include that, and to e raised power j k omega naught n, fine. Then you may rearrange the terms slightly, so I can say x tilde n We'll take 1 by 2m plus 1 outside. Then the summation will exist for the terms that involve k, that is x e raised power j k omega naught, and the exponential e raised power j k omega naught n. Right? Then now you know that your fundamental time period is 1 upon, oh no, it's not t, we represent it by n, that is 1 upon 2m plus 1, and your omega naught is 2 pi by n, which means for this particular case it is 2 pi by 2m plus 1, which means 1 by 2m plus 1 is actually equivalent to, in terms of omega naught by 2 pi. Okay, so we'll make this substitution here. Instead of 1 by 2m plus 1, we will express our x tilde n as 1 by 2 pi, and omega I will take inside the summation, so something like this k is equal to minus m to m x e raised power j k omega naught e raised power j k omega naught n, and then here is my omega naught. Fine. Now we can proceed to limits. We can express x of n as a limiting case of this x tilde n as m tends to infinity, which we had previously here concluded like this. Right? Now that I have expressed x tilde n in terms of my parameters, I can now proceed to limits. 1 by 2 pi k is equivalent to minus m to capital M x e raised power j k omega naught and e raised power j k omega naught n and omega naught, let's call it 2. Now as we proceed to limits, there will be some changes. Fine. First of all, जो आपका ओमेगा नॉट है, it is equivalent to 2 pi here by 2m plus 1, which means as m tends to infinity, omega naught will tend to a very small value. So we can say omega naught tends to d omega, a small value. Fine. And okay, yeah, before proceeding them, let's say delta omega. Then as we proceed to limits, we'll turn summation into what you call integral. Then it will, so anyways, since m tends to infinity, so omega naught will tend to a very small value. We could call that delta omega. Then again, if we make a small substitution here just for the mathematical analysis, if I put omega is equivalent to k omega naught, which then means omega will be k into 2 pi by 2m plus 1. Fine. And we have summation for minus m to plus m. So if k is equivalent to minus m, the lower limit of this summation, then omega will be equivalent to minus m 2 pi divided by 2m plus 1, which means it will be minus m 2 pi. Will take m common here, so it will be 2 plus 1 upon m. This and this will go. Now under this condition, if I use the limits, m tends to infinity. Fine. So iska it will be 2 pi by 2, because m tends to infinity, 1 by m tends to 0, and the sign minus, this and this will go, so it will tend to minus pi. Okay. So with k is equivalent to minus m and m tending to what you call infinity, k will be minus pi. Similarly, when k is equivalent to the upper limit m, and as m tends to infinity, k will tend to pi. Okay. So with this thing, I can just rewrite this equation as limit m tends to infinity 1 by 2 pi summation k runs from minus pi to plus pi x of e raised power j omega. I think we also had a parameter n here. No, sorry, what was my e raised power j, then this will be omega n delta omega. Okay. And as it tends to infinity, your summation will change into an integral minus pi to pi x e j omega e raised power j omega n delta will tend to d omega. Now this is the inverse Fourier transform. So we have basically two expressions. One where we started from this thing. So we have x e raised power j omega equivalent to summation n runs from minus infinity to plus infinity x of n e raised power minus j omega n. This is the discrete time Fourier transform. And then the inverse equation, which helps us to get back our time domain expression from the frequency domain. So it will be from minus pi to plus pi x e raised power j omega e raised power j omega n d omega. So this will be inverse discrete time Fourier transform. Together they form the Fourier discrete time Fourier transform pair. And as a notation, you can simply write it as x of n double arrowed line discrete time Fourier transform like this. Yeah, and the expressions are here. Yeah. Again, you'll see that there's a lot of similarity. There's the way we approached it, it's quite similar to continuous time domain. Okay, but the fundamental difference, it still exists. Continuous time is a continuous function of time, and discrete time, it's a discrete function of time. So it's a good practice. Just try to compare the relations and see if you can find some analysis. There was a lot of similarity, there was a lot of parallelism between the continuous time case and the discrete time case as far as Fourier transform is concerned. But just have a look at the end expressions, whether they are similar, whether there is some change, and that gives you a better understanding of the things. Fine. So like I said, in this course we are mainly interested in the continuous time case, but we'll be doing some properties of the what you call discrete time Fourier transform. That will be in the next video. Fine. So before conclusion, again, although I told you that just try to compare the expressions, and if you remember, for the continuous time case, when we did the Fourier transform, it was quite the reverse. मीन्स जो आपका फॉरवर्ड ट्रांसफॉर्म था लाइक दिस. I think in continuous time, let me write it down here. In the continuous time domain, x of omega was minus infinity to plus infinity x of t e raised power minus j omega t dt. And then the inverse transform was 1 by 2 pi minus infinity to plus infinity x of omega e raised power j omega t d omega. Right? So you see जो आपका transform here, it involves summation, means you will have discrete points in frequency, while as here it was continuous because of the integral. Right? But the reverse is inverse transform. 1 by 2 pi minus infinity to plus infinity x of omega e raised power j omega t d omega. Right? So you see जो आपका transform here, it involves summation, means you will have discrete points in frequency, while as here it was continuous because of the integral. Right? But the reverse is inverse transform. here also you have the integral, here you also have the integral, right? Anyways, this is just for comparison. We'll stop this video here, and next video we will try to discuss some properties of the discrete time Fourier transform. Again, they will be quite similar to those that we did in the continuous time case, but we'll see if there are some properties that are unique to discrete time Fourier transform.